Yes, sir. Can everybody hear me? Hey, guys, I'm live and in stereo. Yes, yes. Thank you so much for taking out time on Saturdays and Sundays during your quote unquote summer holidays. Remember, these days are gonna pay off. The hard work and the effort that you're putting in right now is gonna pay off later on when it comes to university admissions, when it comes to giving your SATs later on. You'll have ample time to do that because you'll already be done and dusted with the syllabus, and you'll be so Gucci with your concepts that all your friends are going to be just jealous, and then they'll be catching up with you guys by watching my recorded lectures. And maybe I don't get a chance to teach AS level ever again. So this is a golden opportunity. This is my model batch. That's why I'm teaching you guys everything and anything that I feel would help you with your concepts. Sir, by end of August, how much syllabus will be covered? Bilal, chill out. Chill. It's a 6 to 7 month course, so hopefully it'll be done. Everything will be done in 7 months. So you don't have to worry about end of August, end of September. Some chapters take a lot of time. Like this chapter and the chapter after this will take even more time than this because it's basically a bridge between O levels and AS level. So that's the bridge that I have to create. And that's why I'm taking things slowly, and I'm taking things with a lot of conceptual understanding. So school starts on the 25th, so I was just thinking how much flex would it be. Bilal, don't worry, you'll have, when you start telling your friends about the periodic table approach and the different ways and how the orbitals look like, you'll already have your flex. Don't worry about that. Even in front of teachers, you'll already have it. But don't teach your teachers this trick. Just do it on your own. Teach your friends, don't teach your teachers. Because they don't want to learn. They are budde babe. Most of them. PhDs, my bum. Sorry, guys. Okay, let's start. So, will we take a break in October-November session? No. Why will there be a break? Okay, without further ado, let's just start. Can I have a Gucci in the chat box? So we started off with electronic configuration, and the last thing we learned was the periodic table approach, And when I talk about the periodic table approach, I basically told you guys that the periodic table is divided into blocks, It's divided into these beautiful blocks, the S block, the P block, and the D block right here, and this is your F block, And if I want to number it for myself, that's your 1S block, that's 2S, that's 3, that's 4, that's 5, that's 6, and so on and so forth. And then if I start with my P block, remember, P starts with principal quantum number 2. So that's 2, 3, 4, 5, 6, and so on and so forth. And D starts with principal quantum number 3. So that's 3D, 4D, and this is obviously then my F blocks which come here, but nobody even cares about the F block, right? Now, because you won't be tested. If I ask you, can you write the electronic configuration of nitrogen, you'll say, hey, it's 1s1, 1s2, 1s2, 2s2, 2p, 1, 2, 3, 2p3. So it's for nitrogen, it's 1s2, 2s2, 2p3. And there was one other way, which was a technique taught to you guys by your teachers, and with a lot of, rote learning, which looks it's a trick, if you want you could use that, but I prefer using the periodic table approach because it's so easy, because even you also have to write shorthand electronic configuration. This is the trick that your teachers must teach you in your AS level. You'll see that once your school starts, they'll write 1S and then 2S, 2P, 3S, 3P, 3D, 4S, and then say you'll fit it like this, diagonally. Fill 1S, then 2S, then 2P. So I don't have time. If somebody tells me to fill out, 37 electrons, I won't have time to just fill this out, then this. I first write all of this, then start filling this. If you want 37 electrons in an atom, that means it's also a beautiful element with 37 protons. Right here, it's rubidium. So if I want to write rubidium, I'll write the shorthand electronic configuration, which is what? Write the noble gas before it, which is argon, and then write the noble gas before it, and then it's what? 5s1. So it's argon 5s1. Gucci stuff? Easy. How easy, huh? And if you want to write the proper electronic configuration, you could say it's rubidium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, but I will first fill the 4s, but I'll write 3d first. So 3d10, 4s2, 4p6, 5s1. That's the proper electronic configuration if you want to write that good stuff, right? But for now, let's just stick to nitrogen, Nitrogen was what? 1s2, 2s2, and 2p3. So these were multiple ways of writing the subshell electronic configuration. Remember, in the exams, we always write the subshell electronic configuration unless and until it's specified, to write the principal quantum number shell electronic configuration, which we've learned in our O levels and IGCSEs. You know, if you want to write the principal quantum number, this is principal quantum number 1, it has 2 electrons, and that's principal quantum number 2, and that has how many electrons? 2 plus 3, that's 5. So principal quantum number 2 has 5 electrons. So in total you have 7 electrons right here, you know. That's the principal quantum number, in which you look at these 1 or 2 or 3. If I want to write the principal quantum number electronic configuration for maybe rubidium, it's never going to be asked. But if I want to write it, let's first write the subshell electronic configuration. So it's 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2 is filled first, but I'm going to write 3d10 because that's a part of your syllabus. It just clubs principal quantum numbers together if you're giving Cambridge papers. If you're not, then it doesn't really matter. You could write it as it is, 3p6, 4s2, and 3d10. It's your choice. And then what do we have? After 4s2, 3d10, then you have 4p6 and 5s1. So 4p6, and this is, remember, this is not in your course. You won't be asked to write this electronic configuration, but the reason why I'm writing it for you guys, that if, God forbid, you're asked to write the electronic configuration in terms of principal quantum number. So just look at the principal quantum number. That's principal quantum number 1, and in blue, you have principal quantum number 2, in green, you have principal quantum number 3, and in yellow, you have principal quantum number 4, and in white, you have principal quantum number 5. So the first principal quantum number has 2 electrons, the second principal quantum number has 8 electrons, the third principal quantum number has how many electrons? That's 2 plus 6, that's 8, 8 plus 10, that's 18, so that's 18, and then the fourth principal quantum number has 8 electrons, and then the fifth principal quantum number has 1 electron. So this would be the principal quantum number electronic configuration for rubidium. But hey, is it gonna be asked? Probably never, but you should be well versed with it, right? Now, in reality, if I look at nitrogen, this was just a recap, right? If I look at nitrogen, it is 1s2, 2s2, and 2p3. And if I further look into this, you know, in real life, it is very complicated. It's not this easy, you know, writing just subshell electronic configuration as 1s2, 2s2, 2p3, you know. We know that the first 2 electrons are going to be in the s orbital, the second 2 electrons are going to be in the p orbital, and then the third, the next 3 electrons are, sorry, the second 2 electrons are going to be, the next 2 electrons are going to be in the s orbital again, and the last 3 electrons are going to be in the p orbitals, right? So if I were to show you, you know, nitrogen would have the first 2 electrons in the s orbital, the second 2 electrons in the s orbital, but obviously it's in the second principal quantum number, so it's going to be larger in size. It'll be at a higher energy, it'll be larger in size, and it'll be more diffused, the things we learned last time. And the third one, you know, this is 2p3. So if I were to show you 2p3, you know, you have the px, the py, the pz orbitals. So it'll be in the px, in the py, and in the pz, because you know that subshell P subshell actually has 3 orbitals, right? P subshell has 3 orbitals. We all know that Gucci stuff. So if I were to show you these 7 electrons in real life, it's very complicated. It would look something like this, you know. The 2s, this would be the 2s. It would have the 2 p's inside it, you know. That's something like this, you know, something like this. And it would also have the 1s, but the 1s would be covered by the 2s, you know. So that's your 2s, that's your 1s probably, and these are my p orbitals. I'm talking about orbitals, right? So writing electronic configuration becomes easy when you talk about subshells, but actually showing those electrons in orbitals become very complicated. You know, where in the hell would I be able to show you all of these electrons? They are everywhere. So this becomes very, 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 very complicated to show electrons in these orbitals. Yes, you can write the subshell electronic configuration, and that would make sense to a lot of people, but showing them in orbitals becomes very, very complicated. So what in the hell do we do? How do we show electrons in orbitals? Well, that's something called electron-in-box diagrams. Now, what in the hell are electron-in-box diagrams? Electron-in-box diagrams are basically diagrams to help you visualize this stuff, to help you visualize how electrons are basically distributed in orbitals, how electrons are present in orbitals, right? And why do we call them electron in-box diagrams? Because we literally use boxes to represent orbitals. We use boxes to represent, instead of showing you the actual orbitals, we just use boxes to represent orbitals. And we fill out electrons in those orbitals, and we show electrons with half arrows. In Cambridge, in CAIE, we use half arrow to represent one electron, half arrow to represent an electron, half arrow to represent an electron. And the up arrow is to show one type of spin, and the down arrow is to show the other type of spin. This can either be clockwise or anti-clockwise. This can either be clockwise or anti-clockwise. That doesn't concern us. The two type of spins that electrons have doesn't concern us. But we show half-headed arrow to show one electron, half-headed arrow to show one electron. And if I'm showing one up and one down, that means these electrons are they have different spins, right? And if you are appearing in Pearson Edexcel or any other course, they normally use full arrows. They use full arrow to represent an electron. So you'll have to check out your syllabus whether it's acceptable to show full arrows as part of your examination. In Cambridge, they strictly use half arrows. In other boards, they sometimes use half arrows, sometimes they use full arrows. You'll have to check that out in your past papers, right? But in Cambridge, I'm dead sure that it's half arrow, right? Now, how do we fill out electrons in orbitals? Remember when I showed you the example of sodium? That sodium, if I were to write the subshell electronic configuration, it's 1s2, 2s2, 2p6, 3s, and then it's 1, right? 3s1. That's the subshell electronic configuration. But orbitals is something different, because subshells are either orbitals or subshells are combination of orbitals. So the s subshell is the s orbital, the s subshell is the s orbital, but the p subshell is a combination of px, py, pz. So it's 2px has 2 electrons, because orbitals don't have more than 2 electrons. They can only hold 2 electrons because they only have 2 unique spins. So it's 2, 2, 2, and then 3s1. Remember, I gave you guys this idea early on, and now we're going to dive deep into how electrons are filled in orbitals. So if an electron's in the 1s region, how do we know for sure that it's not a part of 1s or 2s or 2s? Sidra, that's a beautiful question. So Sidra is saying, sir, if it's in 1s, how do you know it's in 1s? Can't it be in 2s? Can't it be here? Sidra, the answer to that is it's very complicated. It's very complicated. It's literally so much overlap. There's so much overlap that it's impossible to determine. That's why how do we define orbitals? We define orbitals as regions in space where there's a high probability of finding electrons. We always talk in terms of probability, about 95%, because we can never be sure, Sidra. That's your question, and that's the answer to your question. We can never ever be sure. The day we are sure about that, we'll probably be able to teleport. We'll probably be able to time travel. Electrons are everything in chemistry, So now we're going to look into how we fill out these electrons in orbitals. Obviously, it's very important to understand that we can't use the proper diagrams for it because it becomes very complicated. What do we use? We use electron-in-box diagrams, in which what we do is we show electrons by these arrows. Half arrow up, half arrow down. This represents one type of spin, this represents the other type of spin, right? And we use these arrows to represent electrons, and we use boxes to represent orbitals. That is what electron-in-box diagrams are. Now, please realize that we need to know certain rules in order to fill out electrons in these boxes, right? And those rules are what basically define the distribution of electrons in these orbitals. These are 3 rules, One is off-bow, B-A-U. I think it's off-bow, B-A-U, and that's all. Okay, you guys can check out the spelling later on, I don't care. And then it's Hund's rule, off-bow's principle, Hund's rule, and then it's Pauli exclusion principle. And to be honest, you don't need to know either of these 3 rules or what they say by heart. You don't need to know it, but you need to know it to such an extent that helps you correctly fill out electrons in orbitals, right? Now, what do these 3 rules say? Well, the off-bar rule is pretty simple. Let's fill out sodium. If we talk about sodium, we know that sodium has 1s, it's 1s2, 2s2. I'm talking about the orbitals, right? 2px has 2 electrons, 2py has 2 electrons, 2pz has 2 electrons, and then it's 3s1, right? Oh, I think the net went shit. Okay, so continuing, we talked about, the lights went, so I had to pause, but continue, we talked about how electrons are distributed in these orbitals, right? This is the orbital electronic configuration. Above, we talked about the subshell electronic configuration, but we know that orbitals can have more than 2 electrons. So how can a subshell have 6 electrons? Because it's a combination of the px, the py, the pz orbitals. Done, sir. All Gucci. Now, how do we show these electrons being distributed using electron-in-box diagrams? Oh, sorry. Okay, I haven't shared my screen. Sorry. Cut me some slack, guys. Cut me some slack. Okay, chill. Thank you. Hi. Teri yaadein. No, my bad, guys. So I was showing that this is the orbital electronic configuration, and then this is the subshell electronic configuration. Now we know if we were to write orbital electronic configuration, no orbital can hold more than 2 electrons, right? So how can a subshell have 6 electrons? Because this subshell is divided into, it's a combination of 3 orbitals, px, py, and pz. Done? Recording is on, Mohib. Okay, now how do we distribute them in electron-in-box diagrams? The way we do that is using three principles. The off-bar, the Hund's rule, and the Pauli exclusion principle. What in the hell are these principles? You don't need to know the English for it. You don't need to know the English for it, but I will teach you slowly and gradually how you use these 3 rules to fill out the orbitals, right? So what we do is we show the orbitals in, by these boxes. That's the 1s orbital, that's the 2s orbital, this is the 2px orbital, that's the 2py orbital, that's the 2pz orbital, that's the 3s orbital, the 3px, the 3py, the 3pz, then it's the 3dx, not 3dx, it has multiple, axes. So that's the 3d orbitals, the 5 3d orbitals, and then that's the 4s orbital, the 4px, py, pz. And you'll notice that, it's shown here even that the energy increases as you move from 1s to 2s to 2p, obviously because they're farther away from the nucleus. The 1s is the closest to the nucleus, that's why it has the lowest energy, and that is what this principle talks about. That's the first principle, the off-bar principle. Now what in the hell does off-bar principle state? It's like German for saying building up. It's German for saying building up, and we've already talked about this principle thoda sa, Building up. What does this building up principle stand for? It says that the electrons, the electrons will fill the lowest energy orbital first. So electrons fill lowest energy orbital first. Orbitals first. Why would they fill the lowest energy orbitals first? The examiner is never going to ask you this, but you just need to know the off-bar principle. But I've taught you why it does that. Why do electrons fill the lowest energy orbitals first? Why? It's obviously to minimize, yes, for stability. Mohib is right. And how does it achieve that stability? To minimize the total energy of the atom. So why does this happen? To minimize the total energy of the atom, of the atomarino, and therefore become more stable. Everything in this universe wants to become stable. So Mohib is absolutely right. It's to achieve that stability. Now, how do I fill these electrons in the particular boxes which we are referring to as orbitals? Well, firstly, it's the off-bar principle. The off-bar principle says that first of all, you'll have to fill out the lowest energy orbitals, which is the 1s, then comes the 2s, then the 2p's, and then comes the 3s, right? The 2px, the 2py, the 2pz. Can you guys tell me, out of these 3, which one has the lowest energy? Out of 2px, 2py, 2pz, which of these have the lowest energy? I'm just talking about 2px, yz. Yes, Bilal is absolutely right, even Laiba is right, even Sidra is right, Hasib, I discussed this in the last class. All 3 have the same energy. Remember, the orbitals within the same subshell have the same energy. So if it's the 2p subshell, so if it's the 2p subshell, all the orbitals in the 2p would have the same energy. It's just a matter of perspective. Whether you look at it from the x-axis angle, the y-axis, the z-axis, they all have the same energy, right? So we discussed this in the last class, Hasib. Everybody's right. Awesome. Now, firstly, we use the off-boss principle. So what I'll do is I'll first fill out 1s, then I'll fill out 2s, then I'll fill out 2p, and then I'll move on to 3s, right? So this is the order of filling. First, I will fill out 1s, then 2s, then 2p, and then obviously 3s. And I have to represent electrons with these half-headed arrows, you know, like this. This is one spin, and that's the other spin. But then comes the other rule, which is called the Hund's rule. And you know, off-bow principle, if you want to remember it, I have always remembered it through the lift. What does this lift mean? You know, I think to myself, if I were to go to the third floor, I have to first go through the first, then the second, then the third. So it's like, you know, you start with the lowest energy, you start filling up the lowest energy, just like you go in a lift. You start from the ground floor, then the first, then the second, then the third, and you know, that's how you move. You know, so I call this the lift principle. That's my own word for it. If you want to remember it like that, that's up to you. Then comes the Hund's rule. Now, what in the hell does Hund say? Hund's rule, I call it the 3-chair in a bus rule. This is my terminology for it, and you'll never be asked this. You'll never be asked to explain the Hund's rule, the off-bow principle, the Pauli exclusion principle. You just need to know how to use them. So I call this 3 chairs in a bus rule. And you can even explain it to your teachers. What does 3 chairs in a bus or 2 chairs in a bus mean? 3 chairs or 2 chairs, whatever happens, right? Let's just call it 3 chairs in a bus. 3 chairs or 2 chairs. I have a question for you guys. If there are 3 chairs in a bus, and let's suppose Ali is an electron, Ajmal is an electron, and who else do we have? Alaina is an electron, right? Ali, Bilal, Alaina. There's no Ali. Ishal. Okay. Ishal, Bilal, Alaina. These are 3 electrons, right? And you also have... Okay, we'll talk about the others later. Now, you have 3 electrons. Bilal, Alaina, and Ishal. Now, these 3 electrons or these 3 people need to sit in a bus which have 3 seats, you know. It's the same role, like just like in an airplane. If you've ever sat in an airplane, it's like, you know, you have in the economy class, you have 3 seats right next to each other. Now, my question is, will Alaina sit here? And then obviously you have Ishal, and then you have, you know, let's take somebody else. Sorry, Bilal. Let's take Laiba. So Alaina, Ishal, Laiba. My question to you guys is, if there are 3 seats, will Alaina and Ishal sit like this together, or will Alaina sit in one seat and Ishal will sit in the other seat and Laiba will sit in the other seat? Or no, will they all 3 would sit in the same seat? Is it possible? All 3 sitting in the same seat? Well, it is possible, but they'll never do that, because they'll say that, oh my God, there's a chair free, there's a chair free, there's a chair free. So I'm going to fill out this chair, I'm going to fill out this chair, I'm going to fill out this chair. Instead of sitting together, we will fill out separate chairs. We don't like each other. You know, why sit so tightly with each other when we could have 3 chairs? You know, when we could have 3 separate chairs. So what they do is they sit in 3 separate chairs, and that is what Hund's rule says. 3 chairs in a bus. Hund's rule says that if there are empty orbitals, in a particular subshell, electrons will occupy empty orbitals before pairing up. What does this mean? Let's suppose there's, you know, Ishal and everybody else. There are 3 other people. You know, we know that the orbital or the chair can only hold 2 electrons at max. Now you have 3 more people. So now where will these 3 more people go? One guy is going to come here, the other guy is going to come here, the other person is going to come, the other fella is going to come here. Now they are going to occupy, and you know, the same subshell, and they're going to pair up. So before you only had 3 electrons. The 3 electrons would first go into the empty orbitals before pairing up with another electron. Right? So let's suppose you have 2 orbitals. You know, this is the 2px, and that's the 2py. My question to you is, if you have 2 electrons, how would they pair? How would they be distributed in these orbitals? Would they be like this, or would they be like this? 2px would have 1 and 2py would have 1. Yes, Laiba is right, Hasib is right. They'll be like this. So, you know, they hate each other, because you also know that electrons repel each other. Electrons in the same orbital will repel each other. So if you make them come together in the first place, that wouldn't be feasible energetically. That's not feasible. So that's why they'll occupy empty orbitals first, and then majburi hogi, then Laiba is gonna come knocking to Ishal's chair and is gonna say, Ishal, let me sit with you. I don't have enough money to. I'm gonna pair up right here. So then Ishal comes here, and then Laiba go, another Laiba 2.0 goes here, So first they'll fill out the empty orbitals, and then they're gonna pair up. If there are more electrons, then they will pair up everybody, right? So that's what the Hund's rule says. And then the Pauli exclusion principle. What in the hell does the Pauli exclusion principle says? Pauli exclusion principle says that there are two electrons at max in the same orbital, and they are gonna have different spins, or they'll have unique spins, which means one is going to be clockwise or anti-clockwise, or the other one is going to be clockwise or anti-clockwise. So if one is clockwise, the other one will be anti-clockwise. If one is anti-clockwise, the other one will be clockwise. And that's how we represent the spins. This is a different spin, and that's a different spin, everybody. Now, all these three principles and rules, they come together to help you fill out electron-in-box diagrams. And once we do a lot of practice, you will be able to understand it, right? So I call this the lift principle, the three chairs in a bus principle, and Pauli exclusion principle, I call this the spin principle. Because realize that you can have more than 2 electrons in the same orbital. And the reason why you can have more than 2 electrons in the same orbital is not in your course, but there can only be 2 unique spins. One will be clockwise, the other one will be anti-clockwise, right? Okay, Laiva, that's a very good question. So Laiva is saying, sir, if there are 3 chairs in a bus, and Laiba is sitting here, Ishal sitting here, and Ali is sitting here, will they all have the same spin? Yes, they will occupy the orbitals with the same spin, parallel spins. They will all have parallel spins, right? You could have even written it like this. It doesn't really matter, but the convention is drawing the up spin first. The convention is to draw the upward arrow first. This and this is the same thing. You could have easily, easily written this or filled out the orbitals with a down spin, all 3. But the convention is using the up one. You can't say this. You can't do this. You can't say, oh, the first will come here, the other one will go here, the other one will go here. No. Whenever you fill it, you'll have to fill out with the same spin. They'll all have parallel spins. That's a part of the Pauli exclusion principle, right? So this is wrong, and that's correct, and that's also correct, but this is more correct because this is the convention, right? Now let's use all of these 3 to fill out sodium's electronic configuration right here, right, in orbitals. Okay, so the first one is 1s2, so the 1s electron is going to go here, and should I move on to the 2s, or should I fill out the 1s first? Remember, you'll have to first fill out this. If you have a principal quantum number, that will be filled out first. So if it's the 1s orbital, you first of all have to cater to the 1s completely, in totality, the 1s subshell, right? So first we'll look into 1s subshell. I put 1 electron here, and then I couldn't move on to the 2s because I had to fill this out first. So I filled this and then this, right? Then I moved on to the 2s. I filled this here, that's the upward arrow, and there's no other orbital here. The 2s only has 1 orbital, so I'm going to complete this orbital right here. That's the 2s2. And then I'll move on to the 2p. Now, how do I fill out 2p? I'll first fill out the 2px, then the 2py, then the 2pz. Remember, you can't pair them up initially. Initially, they'll go on to different seats. 2px, 2py, 2pz, and then you pair them up. So now you pair the x, y's, and z's with Laiba, Ishal, and Mishal, and whatnot. Right? That's that. And then once you have no more orbitals in this particular subshell, then you move on to the 3rd orbital right here. So now the 3s only has 1 electron, and that's the electronic configuration that you will be asked when you talk about electron-in-box diagrams. So these are the 3 principles. First of all, see, we followed all these 3 principles. We complied with all of these 3 principles. What were these 3 principles? The lift rule, which was first fill out the lowest energy orbitals. And we did that. We first filled out 1s, then 2s, then 2p, then 3s. Good stuff. Hund's rule, which is 3 chairs in a bus. So Hund's rule did not apply to 1s or 2s because obviously you don't have multiple orbitals. But in 2p, you have multiple orbitals. So first you fill out them separately and then you pair them up. Hund's rule complied. Pauli exclusion principle. If you have 2 electrons in the same subshell or in the same orbital, they'll have unique spins. So This one and this one has unique spin, this and this one has opposite spin, this and this has opposite, this and this is opposite, this and this is opposite, and Gucci. So all three principles need to be complied with to write electron inbox diagrams. Now in your course, the same electron inbox diagrams can also come like this. And they can also ask you, this is the 1s, that's the 2s, that's the 2p, this is the 2px. You can write 2p here, that's the 2p subshell. And this is the 2px orbital, the 2py orbital, the 2pz orbital, and that's the 3s. You can even write it like this in your exams. Instead of showing it like this, you can also write it in a straight line. But you need to know that first you have to fill out the lowest energy ones. So for sodium, I first fill this out, then that's good stuff. And then how do you fill out the 2p? The 2px, the 2py, the 2pz, and then we pair them up. X, Y, Z, and then the 3s. Done stuff. So this and this are equally correct. In Pearson and Excel, normally, sometimes they also give it to you like this. So you need to know how to fill it like this, or you can also fill it like this. Normally in Cambridge, this is tested. They just give you straight lines. But you need to know, are all of these at the same energy levels? Are all of these at the same energy levels? Are all of these orbitals? No. So just being in one line does not mean they are in the same energy levels. This is at the lowest energy level. This is higher than 1s. 2p is higher than 2s and 1s. But all the electrons in 2p are at the same energy level. So this 2px, 2py, 2pz, they are at the same energy. And then 3s is above this, like this. If you want to visualize the energy levels, that's how you can visualize it. Done stuff? Okay. Now what I want you guys to do is, for the first, and I will wait only 10 minutes. Only 10 minutes. I'm giving you guys this task. Remember, this is a model batch. So I'm going to do everything with you guys. For the first 23 elements, write down the electronic configuration, which means the subshell electronic. Whenever you're asked electronic configuration in AS level, that's the subshell electronic configuration. And also, okay, I don't want the electron thing. You guys can do that. I want the orbitals filled. Fill out the orbitals. Fill orbitals. Do you want to do subshells as well? Okay, and subshells. Can I give you guys this as homework? Can I give you guys this as homework, or do you want to do it right now? Let's try. Let's see whether you guys can, how many can you guys do in the first 10 minutes. Only for the 23 elements, the first 23 elements. That's what we've done up until now. That's what we've done. And you could literally just use the periodic table for that. Literally. So once you guys do that, then we'll move forward. So I'll give you 15 minutes. 15 minutes, good stuff. I'll also pause the recording and start doing it here. Right? I hope you guys have written the electronic configuration, and I hope it tallies with this. If it doesn't, then you guys can check it out. I've written till the first 22. You can write it till the first 23, right? And the electronic configurations that we've written up until now, that's called the ground state electronic configuration. And I'm giving you guys this extra concept because it may be tested, it is tested in AS level once, but the reason why I'm giving you guys this concept is to explain to you guys the problem with the 24th element. That's the last exception with the 24th element, right? And the 28th, I think, yeah. So if I talk about the ground state electronic configuration, what is the ground state electronic configuration? Whatever we've done up until now, that's called the ground state of the atom, right? Now, what in the hell is ground state of the atom? Ground state of the atom is when electrons occupy the lowest energy levels. That's it. And that's what we've been doing. We've been following the Aufbau principle. Ground state of an atom is when electrons occupy the lowest energy level. Sir, when making the boxes, do we have to label 2px, 2py, 2p? It's up to you, Abdul Rahman. If you want to label it like this, 2px, 2py, 2pz, it's up to you. But normally the examiner doesn't do that, and the reason for that is the x-axis, the y-axis, the z-axis, it's all a matter of perspective, how you look at things. Now, all of this type of electronic configuration is called ground state electronic configuration, right? Ground state of an atom. And ground state of an atom is when the electrons occupy the lowest energy levels, aka they follow the Aufbau principle, right? Now, there's a problem. Sometimes you can also have excited. Now, excited states aren't a part of your course, but the reason why I'm teaching this is because I want you guys to understand, properly conceptually understand the 24th element problem. So there's something called excited states of electrons, in electron-in-box diagrams, Now, what are excited states, and why do we need to know about it? We need to know about it in order to figure out what the hell is the problem with the 24th element. But what in the world is excited state of an atom? Why am I saying electrons? Excited state of an atom. Excited states of atoms. Now, excited state of an atom is when electrons, what they do is, electrons can, they can absorb, yes, Sidra is right, they are more energetic, yes. So what happens is electrons absorb either thermal energy or electrical energy, whichever one it is, we don't care. You'll learn that in university level, how it happens, what it happens. But electrons can actually absorb either thermal energy or electrical energy, and they can be promoted to a higher energy orbital. They can be promoted to a higher energy orbital. That's what the excited state of an atom is. They can either be promoted to a higher energy orbital, or they can be promoted to a higher subshell, or they can be even promoted to a higher shell. So it's either or. You can have the electron go into a higher energy orbital, a higher subshell, or a higher shell. What this means is, let's suppose I'm saying you have the 2s and that's the 2p. That's the 2px, that's the 2py, and that's the 2px, that's the 2py, and that's the 2pz. Now, what I'll do is, the electrons were only here. The 2px, 2py, 2pz were empty. Which electronic configuration is this? 1s2, 2s2. That's the electronic configuration. If the 2p is empty, that means, and the 2s is filled, that means it is 1s2, 2s2. And which element am I talking about? Which atom? That's helium, right? Helium is 4, if I'm not wrong. Is it helium or no? It's not helium. Sorry, my bad. It's not helium. Sir, AS padha rahe hain aur ye haal hai. It's not helium. What is it? It's beryllium. B is 4. I thought, I imagined this 4. I don't know, for whatever reason. So that's beryllium right here. So that's, the electronic configuration of Be. Done, sir? It has 4 electrons. Now, if I want to move the electrons to an excited state, if I want to move if I want to make this atom in its excited state and not the ground state. See, this is the ground state. How am I saying this is the ground state? Because the electrons have occupied the lowest energy levels, right? They have occupied the lowest energy levels. So sometimes the examiner asks you, what in the hell is meant by the ground state? You say that the ground state of an atom is where the electrons occupy the lowest energy levels. And that's what has happened. All the electronic configuration that we write is for the ground state of an atom. But what I can do is, I can provide these electrons with energy, either thermal energy or electrical energy, and I can move this electron. This is the 1s, right? I can move this electron to the next subshell. I can literally have, this would be this, and this would be here, and I can move it here. I can move this electron right here to here, literally. Yes, that'll be the excited state of the electron. That'll be the excited state of the electron, right? Now, what I can also do is, I can also take the 1s electron and move it in the 2py. I don't care. I can do that. How is it possible? Well, I just provide it with energy. I can provide it with thermal energy, electrical energy. I can take this electron and I can move it to the 2py. It'll still be the excited state. Yeah. So if I give you more and more examples of this, you'll understand the difference between ground state and excited state. Let's suppose I talk about maybe silicon. Let's suppose I talk about Si. Si is 14, right? If I'm not wrong, it's 14. So if I start filling it up, 1s, 2s, it's 1s2, 2s2, 2p, x, y, z, and then you pair it up, 1, 2, 3. How many have I filled? That's 4, 4 plus 6, that's 10. And then we move on to the 3s2, and then we move on to the 3p. It's 1s, 2s, 2p, 3s, and that's 3p right here. And 3p has how many electrons? Only 2. That'll be equal to 14, right? So 2, 4, and that's 6, 10, 12, 13, 14. Good stuff. How much energy? Not a part of our course. It varies. I don't care how much energy. But if I say I have the same stuff, I have this is the ground state electronic configuration. Now I'll take this ground state electronic configuration. I'll take the ground state electronic configuration. Let's suppose let's see if I can duplicate this stuff. Yes. I'll take the ground state electronic. Ye kya ho gaya? Oh my god, I hate this duplication. What in the world is the problem with this? Please work, please duplicate. I can't be bothered. I can't be bothered to write this again. Okay, it don't matter. I'll just show it to you. What I can do is I can take this electron. What if I take this electron, or if I take this 3s electron and move it here? Would it be excited state? Absolutely. It's against my it's not following my rules. Now the electrons are not occupying the lowest energy orbitals. They aren't occupying the lowest possible orbitals, energy levels. They aren't. I'm literally taking this here and moving it here. Do you write the electronic configuration like this, where you only have one electron in the 3s and 3 electron in the 3p? No, that's called the excited state of the atom. That's called the excited state because it doesn't follow the principles of ground state. You've provided the electron with energy or thermal energy or electrical energy, doesn't matter, but you've moved it to a different orbital or a different principal quantum number even. I can move this 3s electron to the 4s. It doesn't matter. I can take this electron and move it to the 4s. That'll be the excited state. So remember, when the principles aren't being followed, when the electrons are not occupying the lowest possible energy levels, that means it's in the atom is now in its excited state. The atom is no longer in its ground state. My question to you guys is, and this is what a lot of teachers get wrong even. My question to you guys is, what if I take the 3px and move it right here to the 3pz? Would it still be the ground state? Something like this. Move this here and move this here. So this would be there and this would be there. Everybody's right. See, this is what I mean. This is what I mean when I say give the students concepts. They'll figure it out on their own. You guys are right. You guys, I think, sir, but 3px, 3py, 3pz, they're all at the same energy level. It's still a ground state, remember. So this is also the ground state. You're going against convention by not, filling this. You're going against convention. That doesn't really matter as long as you have the electrons in the same energy level. That's good. That's Gucci. You guys have got the point. But what if I take the 3p electron and I fill this out like this, and then instead of filling the 3py in the same parallel spin, I occupy it with the opposite spin like this. Will this now be the excited state, or will it still be the ground state? Yes, now it will be the excited state because you know that all electrons should have parallel spin in the same, if they are singly filling out the same orbit, these three orbitals. So they should be, if they're singly filling out these orbitals, they should have the same parallel spin. But now you're messing with the spin. You're providing it with energy. That's why it has the opposite spin. So this is excited state, and this is still the ground state. Yeah. Because 3px, 3py, 3pz, they're all at the same energy level. Awesome. Now, did you guys need to know these differences? No, you didn't. But why did I tell you this? Well, I taught you guys this is, the reason why I taught you guys this is because there's a problem with the 24th element. And this problem is what I called the periodic table error. The periodic table error. And that's the only error that the periodic table approach is going to give you. Only error. No other error, so you guys can remember this exception. Now, what happens with the 24th element? Can you guys write the electronic configuration for chromium? Chromium is the 24th element. Can you guys write the electronic configuration of chromium? Just write the shorthand electronic configuration for it, not the full electronic configuration, just the shorthand. Just the shorthand. That's the last concept and we're done with electronic configuration. What's the shorthand electronic configuration for chromium? Do you want me to do it for you? Or can you guys do it on your own? Where's the periodic table? So chromium is right here. This is chromium. So if I were to write the shorthand electronic configuration, it's argon, it's argon 1, 2, 3, 4. 4s2, 3d, 4. Isn't that right? So I'll write argon 4s2, 3d4. This should be the ground state electronic configuration as per the periodic table, shouldn't it? Is everybody agreeing with me here? Shouldn't it? Should this be the ground state electronic configuration of chromium? It should, You've literally followed the same principles that I've taught you up until now. It should be. But the reality is, it isn't. That's the error. That's the exception. Not the error, the exception. In reality, what happens, listen to me very carefully. I'm giving you guys the concept. The concept is not in your course. Please realize this. But if you guys understand the concept, you will be, on top of everything, on top of every concept. Okay. Now, what happens is that science, they somehow proved that this, in fact, you used the periodic table, you used all the methods that you learned, but this, in fact, is not the ground state. It's not the ground state. This, in fact, is not the ground state. Now, what in the world is the ground state? Well, the ground state is you take argon, you take 3d, and you take 4s, and you move one electron from the 4s to the 3d, because you'll realize how are the 4 electrons in 3d arranged. They are 1, 2, 3, 4. You have 5 3d orbitals, and in the first case scenario you had 4 electrons, and 1d orbital is empty. 1d orbital is empty, and what happens is that one electron from the 4s moves to the d and makes it filled. And please realize that a half-filled subshell, this half-filled subshell is more stable than A right here. So the B electronic configuration is more stable than A, right? And if it's more stable than A, what does that mean? That means that in B's case, the overall, because more stable means it has lower energy. So overall energy in B is actually lower than what? Is lower than A. Make sense? Overall energy in B is actually lower than A. So would I call A ground state or would I call B ground state? What I call A ground state, half-filled subshell, half-filled orbitals. It doesn't really matter. You could say half-filled d orbitals. Half-filled d orbitals, you could say. Half-filled d orbitals are more stable. Now, is B the ground state or is A the ground state? If the overall energy of the atom is lower in B, that makes B ground state. Because what is ground state? Ground state is when electrons occupy the lowest possible energy levels. And the lowest possible energy levels would make it more stable. So if I'm saying B is more stable, that means B is the ground state because electrons are actually occupying the lowest possible energy levels. Right? And that makes it more stable. So if the examiner asks you, why do you fill it out like this? Why not 4s2 3d4 like the periodic table tells you? Well, the reason is because half-filled d orbitals or half-filled d subshell is more stable than the one given above. So half-filled, this is what you tell the examiner, half-filled d orbitals or d subshell, doesn't really matter, is equal to more stable. Hence, B is ground state. Yeah? So that's the electronic configuration for it. Now, did you need to know this? Did you need to know this? No, you didn't. Did you need to know this? No, you didn't. So in reality, what happens is that the electron is basically promoted from the 4s to the 3d, because 4s was at a lower energy level than 3d. So if you were to give the electrons to 3d, that's why you fill out 4s first, right? So one of the electrons is just it just goes from the 4s, the s orbital, to the unfilled d orbital. Why? Because that's the ground state now. अच्छा, अब ये क्यों होता है? Why does this happen? Why does this happen? To minimize the total energy of the atom. You guys don't need to know all of this stuff. What do you guys need to know? You guys just know half-filled d orbital is more stable, hence B is the ground state. Therefore, this is the correct electronic configuration, not this. That's it. That's all you need to know for your exam. Right? And similar is the case with copper. If you look at copper, what is copper? And you can say half filled or full filled, fully filled d subshell. Half filled d subshell or fully filled d subshell. Orbital carries sub, it's better to say subshell, to be very honest. It's better to say half filled and full filled d orbitals or d subshell. It's the same thing. Half filled or full filled d orbitals, put an S, or just say half filled or full filled d subshell. Right? Okay. So it can either be half filled or it can be full filled. It'll have an overall lower energy. My question is, what's the problem with copper? What's the problem with copper? Should it be the same for Mn, Fe and Co? No, I'll tell you why it's not the same for Fn, Ni and Co. Why? Because you talk about Mn is already 3d5. Mn is already 3d5, kiddo. Mn is already 3d5. So this only applies to where one electron can either make the d subshell filled, or one electron can fully filled, or one electron can make the d subshell, the entire d subshell, singly filled. Right? So when does this happen? When one electron can make the d subshell fully filled or singly filled. Only one electron. Now if you talk about Mn, if you talk in terms for Mn, that's 3d1, 2, 3, 4, 5, and you have 4s2, right? And write 4s2 here. Now, if I take one electron and put it in 3D, that'll be the excited state. That'll not be the ground state, because this one electron is not making this half singly filled, this entire d subshell, or this one electron is not making the entire d subshell fully filled. So if one electron can do that in case of chromium, what happens in chromium? One electron is making this entire d subshell singly filled. So if one electron goes here, now this is beautiful. This is more stable. So singly filled d subshell is more stable than, than the one given above right here. So this is actually the electronic configuration of chromium, not this. This is what happens, not this. Yeah. Acha, what I was saying was that for copper, if you look at copper's electronic configuration, can you guys tell me the shorthand? So argon, and this is 4s2, and it's 3d1, 2, 3, 4, 5, 6, 7, 8, 9. So 4s2, 3d9. So I'll write first 3d. 3d9, 4s2. Done, sir? My question to you guys is this the correct electronic configuration? Remember, singly filled d subshell or fully filled d subshell has an overall lower energy level. Has an overall lower energy. So it would be argon 3d10 and 4s1. Absolutely correct. So this is wrong, Hasib. You're absolutely right. It should be what? Argon 3d10 and 4s1. So this is the correct electronic configuration. Why? Because see, one electron can actually fill out the entire d subshell. So this was 4s2. This is d1, d2, d3, d4, d5, and this is d6, 7, 8, 9. And if I move one electron here, the entire d subshell will be fully filled, right? And that's the beauty of it. So if I ask you what's the electronic configuration for copper, this is the electronic configuration. And this you can't catch through the periodic table. You can't, because the periodic table will tell you it's 3d9 4s2, but you need to use your brain. Whenever a d subshell can be fully filled, that's more stable, which means that'll actually be the ground state. This is actually the excited state. This is the ground state, because this has an overall lower energy level, lower energy of the atom. Yeah? This is the excited state. This is the ground state. इतनी डिटेल आपको पता होनी चाहिए थी? No. You did not need to know any of this detail. What you guys needed to know was, if you were to fill chromium or copper, you're going to say argon. This will be 3d5, 4s1. And if you want to say copper, it is 3d10, 4s1. And examiner says you should remember it, memorize this by heart. There's no why. There's no why. Yes, you are right, Hasib. Yeah, that's not in your course. Absolutely, but it would be the same for it. Yeah, absolutely. Absolutely it would. Absolutely it would. Absolutely. That's why I'm not going above this. Yeah? Maza aa raha hai waise. So examiner says, learn this by heart. But I'm saying, never learn this by heart. Never learn this by heart. always know the idea behind it. So the idea is the idea of ground state and excited state. So whenever the examiner asks you why is it like this, because this is the ground state and gives an overall a lower energy, this gives a more stable atom, wherein it occupies the lowest possible energy levels, whatever. You can write all of that. Is it possible for the opposite to happen? Can electrons lose energy? Yes, Sidra, it's also possible. It's possible. Electrons can definitely, yes, you can have 4s3. You can't have 4s3, but they can definitely lose energy. And you know what happens, Sidra? When electrons gain and lose energy, do you know what happens? Do you want to know what happens? That's a part of your A2 level, if I'm not wrong. Well, in A2 level, they won't teach you this, but I'll tell you. See, electrons gain energy. Let's suppose an electron was here, and you made it gain energy and it came here. Now the electron, this is not stable. This is the excited state. You provided it with the energy. So the electron is going to fall back to this level. Again, let's suppose this was 2 joules. I'm just assuming values to make it easy for you. And let's suppose this is 5 joules. So you made the electron go from 2 joules to 5 joules, but this is not a stable state. This is the excited state. So what's going to happen is, this is only momentarily. This electron is going to fall back to the ground state. So you gave it 3 joule energy, and it will release that energy and fall back to the ground state. And you know what happens when it releases energy? That's how you have light. That's how you get light. These different colors. It gives out energy in the form of light. How much energy does it give you? The difference between these two orbitals. If this is 5 joules, this is 2 joules, so the difference that it gives you is 3 joules. That's why transition metals give you lights as well. So once the electron is promoted to the outer orbit, that's not that very much stable, it falls back. And so when it falls back, it gives out that energy in the form of light. That's how you get light. Literally. Makes sense, everybody? Maza aa raha hai? This was it. Yes, you're right, Abdulaman. It has to do with photons, shotons, but I'll not delve into that. Acha, and the reality is, do you want me to actually tell you the core reality behind it? The core reality, once again, I want to make you visualize this at the end. The core reality. Oh, re sajna. Where is the core reality? Right here. So what happens is that, let's suppose chromium. Let's talk about chromium. So chromium was 4s1 and 3d5, because singly filled d subshell is more stable. That's all you need to write. Singly filled d subshell is more stable. Acha. The reality is that what happens is that when the 4s gives the electron to the 3d, electron is promoted right here. Yes? Electron is promoted. I'm saying this is more stable. The electron promotion is more stable. But realize that if you're providing it with energy, shouldn't this be the excited state? Well, sir, you told us that this isn't the excited state because it has an overall lower energy and therefore it's the ground state. But you guys did not ask me, this is true, but you guys did not ask me this, why does it have an overall lower energy? Do you know why it has an overall lower energy? The reason is when you promote this electron, and listen to this very carefully, it's not in your course. Bas ab khatam ho gaya chapter, I'm wrapping things up. This is not the reason why it has overall low, why it gives you overall lower energy. Why does it give you overall lower energy? You're literally taking the electron and placing it here. So the atom should have overall higher energy. Sir, how does it have lower energy? Why is it making it more stable? Why does it have overall lower energy? Because when you promote the electron to the 3d5, it is more stable. Why is it more stable? Because once you promote the electron, let's suppose I gave it 2 joules of energy. Do you know, once it's promoted and it forms this electronic configuration, it gives out more energy than you require to promote it. So you promoted it by using 2 joules of energy, and once it's promoted, the entire orbital is singly filled now. All the orbitals are singly filled, and this actually gives out more energy than you provided it with. And that's what makes it more stable. So you gave it 2 joules of energy, it gave out 4 joules of energy. So now it dissipated. Dissipated means it lost an extra of how many joules of energy? It lost an extra of 2 joules energy, which makes it at a lower energy level and therefore more stable. Let me make this 5 to make it more clear. Let me make this 5. Let's suppose it gave out 5 joules of energy. So now you gave it 2 joules, but once this electronic configuration formed, it gave out more energy than you provided it with. So what happens is, overall, this is the lowest, this is the ground state. This is the lowest possible lowest energy electronic configuration possible. Why? Because it's giving out 3 joules excess of energy. It's giving out 3 joules energy in excess. It's dissipating that energy. So that is the reason for it. It gives out more energy than is required to promote the electron. That only happens once the d subshell needs to either be entirely singly filled or fully filled. But did you need to know this? Absolutely not. Nothing of this sort. You just needed to know that these two are the exceptions and needed to know this by heart. Khatam? Finished? Now your homework is just one homework. I want you guys to write down the electronic configuration of the first 36 elements of the periodic table. And once you write the electronic configuration of the first 36 elements, I also want you guys to draw the electron-in-box diagram for it. Inbox for it. Yes? So just remember, copper and chromium are the periodic table error. And you guys can use this for electron-in-box, or you could just draw it in straight lines. Doesn't really matter. And you guys can use this to verify your answer. So once you're done, just use this to verify the answer. Okay, and one more thing, guys. If the d subshell has no electrons, like here, it's 3d0, you don't need to write 3d0. You don't need to write it. They've written it for your understanding. You don't need to write. If it's 3p6 4s1, you don't need to write 3d0. It's okay. You don't need to do that. If you do that, it's fine. But if you don't, it's also fine. Okay? Normally we don't write 3d0. If the subshell is empty, we don't write it. Yeah? It's just to show you that this actually exists. It's there, but it's empty. Why? My question to you is, why do we fill out the 4s before the 3d? Why? Why do we fill out the 4s before the 3d? Yes, because the 4s is at a lower energy level. Awesome. And sir, kasam se maza aa gaya. I enjoyed it so much, sir. Absolutely. You guys are right. See, that's the thing. You need to just use your brain thoda. And this is even more complicated. I just used numbers to help explain, but it has to do a lot with electromagnetic chemistry and enthalpy change calculations and frequency and electromagnetic radiation, and all of that you learn at PhD level. I learned it when I was a part of the Pakistan national chemistry team. I learned all of that good stuff, and it hurt my brain. So all of that stuff is not a part. You guys are taking AS level, like a joke, because I am, inshallah, it will be a joke for all of you. I promise that. And we are making it a joke for ourselves. But realize that the concepts that you are covering here are actually university level concepts. Once you're done with AS level, you'll actually, or A level in totality, once you're done with A level in totality, you're actually going to be Gucci and properly, not rote learn things, properly, you'll be done with 2 years worth of syllabus as far as sciences are concerned. So realize, no, in AS level we don't go beyond 36 elements. Even 36 is too much, Hamza. But I am making you guys write 36 because, I'm me. I'll do that, So even 36 is too much. You won't go above 30, but I want you guys to write it till 36. Because I have answers till 36. So you guys can take a screenshot of this later on. Oh, we just did it in 1 hour. We finished this. So electronic configuration, guys, is officially over. Let me see if I have some snippets to show you. If you guys want, what have I written here? Spin is a complex factor, and all you need to know is that electrons with opposing spins have an attraction sufficient to allow them to occupy the same orbital. So this has never been tested and will never be tested. But if you're a Pearson edX student, you could say, if the examiner were to ever ask you why, electrons repel each other in the same orbital as well, because they have opposite spins. But realize opposing spins also has attraction sufficient to allow them to occupy the same orbital. Okay. Cambridge says only till krypton. So this is krypton. This is 36. It is only till krypton. Yeah. So if they ever ask you, why does, this is just exam perspective now, why do two electrons, why can two electrons occupy the same orbital? Can't they repel? Well, they do repel, but opposing spins can actually create sufficient attraction. You know, it's magnetism. That's not a part of your course. You learn that in physics. So opposing spins can create attraction, magnetic attraction, sufficient to allow them to occupy the same. Just like, you know, you have magnetic field cancel out each other's magnetic fields. Yes, Mohib, it has to do with fields and whatnot. So they create enough attraction to allow them to occupy the same orbital. These are just fun facts that I've gathered through all the 20 books that I went through when preparing for this course. What else? Sublevels are made up of orbitals. Remember when I talked about subshells, sublevels, same things. They're what? It can either be an orbital or a combination of orbitals. Yeah. What else? What else do we have? As ground state. Okay, Gucci. I'm just adding all the pictures here, the ones that I've snipped out while reading the books, and I thought, oh, this might be handy dandy for students. What in the hell is this? Yeah, see? That's what happens. The electrons first fill out the 4s, then they fill out the 3d. Yeah. What else? What else do I have? Let's see. Just a couple of things that I want to share with you guys before we leave. The shells are also referred to, the principal quantum numbers, the principal quantum shells, they are also referred to as electron orbits. We know that. I've taught you guys all of this stuff. And this is a summary of how you fill out electron-in-box diagrams. Well, I've told you the three rules, the three basic rules, but if you want the English for it, electrons occupy the lowest available energy level. That we call the off-Bohr principle. Off-Bohr principle. And then electrons only pair when there's no space, when no other space is available in the subshell. Hence, electrons do not pair up until a subshell is half filled. This was the this was the Hund's rule. Yeah. And then in single paired orbital, electron spin is opposite, that's called the Pauli exclusion principle. Yeah. Pauli principle. Electrons in a subshells that are not paired spin in the same direction and represented by, when I told you that all the electrons in, these subshells, if they are not paired, they'll have parallel spins. They'll have the same spins. That's also Pauli exclusion principle. Pauli. And note that the 4s subshell is slightly lower in energy than 3d and is filled first. However, when forming positive ions, 4s electrons are lost first. And we studied that, when I told you the idea behind why. I told you the why behind it even. I taught you guys all of the whys, but the whys aren't in your course. So this is just a summary of how to fill out electron-in-box diagrams. Easy, guys. Any questions? We are officially done with electronic configuration. I just have a question for all of you. My question is, remember when Erwin Schrödinger figured out how the idea, there's something known as sublevels or subshells. Remember when Erwin Schrödinger figured that out? How did he figure it out? How did Erwin Schrödinger figure out that all the electrons in the same principal quantum number or in the same shell, they don't have the same energy? They actually have different energies, because only for principal quantum number 1 they have the same energy, because there's only one subshell. But in principal quantum number 2, he realized that the P subshell actually has a higher energy than the S subshell. And so he realized that if you have, by knocking or by plucking the electrons out, and they require different energy, and that knocking is called ionization energy. That's our next topic, which we'll do tomorrow, 11 a.m. Remember, I've always told you that chemistry is a story. Everything is connected. So tomorrow, 11 a.m. Grape, we'll be doing how Erwin Schrödinger, started to pluck out those electrons, and he proved Bohr wrong. देखो एक challenge है, history है, चल रही है. Yes, it's fun. It's enjoyable. As long as you follow the story and don't miss out on classes, and even if you do, you watch the recordings first before sitting in the live class, you'll be Gucci. So can I see you guys at 11 a.m. tomorrow?